So we left off last class. This was the last slide I left on, and these were the conditions to take a glycosyl sulfide thioether and activate using any of these things with the nucleophile. And we go through an oxocarbenium, which I guess if you have acetates will be C2 anchiomeric assistance, and this will lead to the product, which will be beta because of C2 anchiomeric assistance. Okay. Fun. Just found out my minus 80 freezer is just fucked, so I need to buy a new one. Fun. Okay, I will live. Just literally 30 seconds before I turned off my microphone. So I'm a little suppressed in my mood because I think those things are like $50,000. So if we want to take a glycosyl sulfoxide or sulfide and we want to turn it into something a bit more reactive, because remember when I was discussing this, I was saying that we had this order of reactivity from a glycosyl thioether to a sulfoxide to a sulfone. We got more reactive as we went down. And that the sulfide is actually, the thioether that we just saw is pretty stable. You need these pretty strong conditions. You need almost like a halogen agent plus a strong acid. So if we take, how do we make one from the other? Well, we actually start with that thioether, and we treat this with different things. So one thing we can do is we can treat it with MCVBA, which we have seen lots of times. Minus 30 degrees to minus 80 degrees. Which would be great if I had an ultra low freezer that was working. But you need to do very careful monitoring. This is actually a really irritating reaction because it does work. But it has a major problem. And that major problem is that if you're not careful, RT stands for room temperature. But starting to get anywhere close to room temperature. You get the other one that we wanted, the sulfone, it overoxidizes. So it's very, very easy to take this thing too far and make the sulfone instead of the sulfoxide. I'm not going to draw the mechanism for this. It's exactly the same mechanism you would draw for an epoxidation of a double bond. Except your electrons are not the double bond, your electrons are a lone pair on the sulfur. But it's exactly the other way. Other than that, it's exactly the same kind of reaction. So this is a pain. So there's got to be a better way to do this, and there is. And that's, a reagent that I've never actually seen anyone else use for any other application. It's called MMPP. You do this at room temperature, which is very convenient. And you make the sulfoxide. Okay, so what is this? This is one of those things where you're like, I have no idea how anyone came up with this reagent. It is a peracid, but it's a weird ass peracid. So mechanistically, there is nothing different between this and MCVVA. But it's much less reactive. Now, if you swap that magnesium salt for some other ion, it becomes more reactive. So magnesium attenuates the reactivity of this agent, makes it less reactive, so it doesn't oxidize the sulfoxide to the sulfone. Your guess is as good as mine. The mechanism for this might be known and why exactly it is so gentle, and it's probably not mechanistically, like arrow pushing doesn't differentiate. It's probably just energy differences between transition states. I don't fully understand why this is less reactive. Like I can wave my hands with the best of them, but I don't really convince myself. So we can use MMPP to selectively do this. So if you want to make a sulfoxide, this is probably a better way of going about it. So again, these are pretty stable molecules. They don't come off with just anything. You do need sort of special conditions for the most part, so they survive quite a lot of chemistry. Unless like it's oxidation, in which case they're going to oxidize further to the sulfone. So if we have that, we can activate it using Triflic Anhydride. So we've seen what triflic acid is. Triflic anhydride is just like the oxygen between next to the sulfur is attached to another sulfur for another triflic group. And really, really good electrophile. Just text, the way I've drawn it, there's no leaving group. Kind of like leaves itself. But I'm not going to redraw it. So you make a triflate here. Now, obviously what we've done here is we've gotten rid of that negative charge. And why do we need to use this? Well, triflic anhydride is an amazing electrophile, but sulfoxides are not great nucleophiles because that oxygen is not really all that negative. Like it's partially a double bond to the sulfur. It's not really O minus. Like it is, but it isn't. And so to get that to work, you need a really, really hot electrophile. There is no hotter electrophile than triflic anhydride. Now we've made something where we now have a positively charged sulfur. And it's a true positively charged sulfur. It's not like mediated by a double bond to oxygen that may or may not be there. So it's not that surprising that this rapidly makes an oxocarbenium. And then if you have some nucleophile, and if we're acetate protected again, we're going to use anchiomeric assistance and we're going to deliver the beta product. So again, this is very, very, with the triflic anhydride would not activate the glycosyl sulfide that we saw previously. That's not good enough. You needed those really strong iodines and bromines with the strong acid and sulfur iodine bond because the sulfur was neutral and all that. Here we've got a negatively charged oxygen, but it's kind of like not really negatively charged. So this is a bit more reactive. So where we go next with this is just pissed off. Okay. Is if we have the sulfone. I should never check my email before class. It's just going to depress me. This is the most reactive of all these things. And we make this again by taking the sulfide and treating it with MCPA. Or we could take the sulfoxide and treat it with MCPA. We've got options. And we need something really delicate now, because this thing just wants to fall off. All you need is some magnesium bromide, which in my list of reactive things is not very reactive. You can leave this salt lying around for a very long time and nothing happens to it. It's not really going to react with oxygen in the air. It's not really going to react with water. It's just going to sit there. It doesn't do a whole lot. And of course, the important thing here is the magnesium, not the bromide. Bromide's been important for everything else, but now this is like Br minus kind of thing. It's not Br plus like we saw with the sulfide. These are just Br minuses attached to magnesium. And what we get is the magnesium thinking that I got better things to do than attach to bromide, like I could chelate to 2 oxygens. And of course, as soon as I do that, I'm moving positive charge onto those oxygens. And that means I'm moving positive charge onto the sulfur. And if I'm doing that, then I'm making this guy delta plus. That's turning into a really good leaving group because it's at the anomeric center. So it should be relatively unsurprising that we're going to end up with an oxocarbenium. And then in this case, if we have a nucleophile, we don't have any chimeric assistance. What solvent are we doing? Probably doing this in like dichloromethane. So all else being equal, we're expecting the anomeric effect to dominate. So we expect to get the alpha product.
Sorry, John. For the very first reaction you were talking about with the MCPBA, did you say that if you do it at cold temperatures and you let it go on for too long, it turns into the sulfone?
Yeah.
Okay.
If you get too sloppy, you get over-oxidation because it just starts oxidizing. I think it's because the sulfoxide is only slightly less amenable to oxidation than the thioether ether. So if a fresh MCPA is looking at both of these, it sees them pretty much as equivalent to what to oxidize. And of course, what we want to do is oxidize this, not this. Because if we oxidize this, it goes to product. We just want to make product. So if you keep it nice and cold, you can differentiate those energy barriers enough that you only oxidize the starting material. But if you let it warm up too much, then you start oxidizing. This to this. But the problem, of course, is if you try and do things really cold, then reactions are really slow. So you're always trying to keep it as cold as you can to get selectivity. But then you want to keep it as hot as you can to get reaction rate. Because you don't want to be like minus 30 to minus 80 is a 50-degree difference. So that's on the order of 2 to the 10 difference in reaction rate, which is quite significant. So it's probably really, really fast at minus 30. You start worrying about over-oxidation. At minus 80, the damn thing probably just crawls along really, really slowly. I've never actually done that because I've always used MMPP.
Okay, thank you.
If I'm using MCB on this, I'm just letting it rip and taking it all the way to the sulfone. This works for all sulfurs, like not just sugars, but like any kind, if you need to oxidize a sulfur for whatever reason in your life, as one does. So this is making our 3 different types of sulfur things. What this actually does is it gives us quite a lot of flexibility. So in the recorded lectures I'm going to do next week, I was going to try and do them during this time just in case anyone wanted to show up during reading week, but I won't. I'll do them on my own time and I won't put them live just so there's no pressure at all. I do some stuff with some talking about protecting groups. But let's say we're trying to make a trisaccharide. So So we have that. Let's make this one glucose. And then, I don't know. Yeah, whatever, who cares? I actually just really hate dry mannose, so I'm going to make a stupid sugar, ultrose, I think. So I got 3 sugars. In each case, through you'll see why through selective protection and deprotection, I'm able to make it such that I've liberated 1 OH in each case. And then I want to make this molecule. I haven't thought out how I'm attaching this to anything yet. So it's going to be an awkward way. I'm going to have to draw it like this. So we want to make this trisaccharide. And we've got those 3 molecules because, you arrive in a lab and some postdoc who just got a real job has left and has left you with these 3 molecules. And your boss says, I want you to make a trisaccharide out of this. So we've got a couple of principles I want to discuss here where we can try and figure out how to do that. That's an acetate triggered there. So first of all, what we can take a look at and sort of see what we need to do is we've reacted all the thiophenols. And we've attached A to B to C. And we can even sort of label what the connection is. It's A, beta 6, because it's beta 6 to B. And then C, B to C is an alpha 6. Connection. Okay, that's not too hard. Like all these, I've given you the protecting group strategy, so all the OHs are in place in the right spot. Now the issue just becomes, how do I get these to react together? Because let's say you're thinking, okay, it's a thiophenol. I know how to do this. I take IDCP or I take like MBS and triflic acid or whatever the fuck you want. So I take A plus B and I treat that with IDCP and DCM. I should get AB. The problem, of course, is I can also get BA or BB or AB or AA. Because I can get all those different combinations because I have that thiophenol there. So that's
John,
not.
will by any chance we learn how we selectively protected certain OH groups?
Absolutely. I'm going to try and squeeze that into some lectures next week where I'm going to post some
Okay.
videos on it, on a lot of the stuff, and we'll come back and cover some. Hopefully, what I'm going to happen is you guys are going to take a look at those and watch those, and then we're going to do some problems the first Tuesday back after reading week. So
Okay.
we'll sit down and do some exercise where we try and walk through as a group how to selectively protect things. So go over it.
Awesome.
So go over the strategies you use with different protecting groups in these video lectures. I guess they're all video lectures, but like that's like a real video lecture because I'm not doing it live. And then we will sort of apply it.
Awesome. That's great.
Yeah, no,
Thank
I
you.
think that's actually really interesting, and no one spends enough time on it, and it's a lot more interesting than a lot of this stuff actually. But coming back to this idea, I don't want to get a mixture of four compounds, and this doesn't even include all the alpha beta isomers. So there's 8 possible compounds coming out when I mix A and B together with these things. So what I want to do is I want to favor that. So there's a few ways we can do that. So I'm just going to sketch these in the top here, just so that we're all. Sorry. Damn. I'm trying to think of the best way to do this. Okay, I'm just going to call it A. B is basically the same thing, but ultrose, but doesn't really affect anything. And C, we have a different hydroxyl group protected. I actually made this problem harder than I intended to, because of course I did. Okay. So if I want, so there's a term that we're going to use, reducing sugar, which means sugar at the end. Um, Now, normally that means that that's an OH group on the anomeric position of that sugar, but it's actually the terms become more general. So it means whatever sugar is not attached to other sugars, it's not going to couple on both sides. It's got a free anomeric position. In this case, it's not free; it's got an isopropanol on it, but it's still at the end of the sugar chain. So what we want this guy to be is we want this guy to be the nucleophile, and we want B to be the electrophile in the first step if we're making the AB bond first. Sorry, guys. Give me 1 second. My wife says this is a 5-person class. Whoever cares.
John,
Yeah.
you won't believe this. Just a second ago, I was wishing that someday Dr. Dana will pop up from the door. Oh
Oh,
my
there she
God.
was. Yeah. Okay.
There she was.
Okay. Um, okay. So we have the nucleophile. We have the electrophile. So we want to make the electrophile an electrophile, so we want to make an oxocarbenium. The problem is any way to make an oxocarbenium of B is going to make an oxocarbenium of A as well. And if we have the two together, so that's an issue. The other issue we have is A and B are both pretty good nucleophiles. Like the OHs are the same. So ideally, we want to make one more reactive than the other. And we have 2 different ways we can do this. One way is we can play around with the sulfide oxidation state. ways to differentiate. I'm just going to change color. It's a lot more fun. Well, it's a lot more fun when a dog comes charging downstairs because I'm really not expecting. He's not allowed in the basement. It doesn't stop him because I don't set the rules. So, sulfide oxidation state. So one thing we can do with B then is to make B more reactive. We can take B, we can treat it with MCPPA at room temperature. And then, of course, what we'll get is that. So now what we've done is we made a much better electrophile, right? Because if we take A and B now, this is kind of going to cause B prime. So if we take A and B prime and we have magnesium bromide, A is going to ignore that, right? Like that, the thioether ether on A is just going to go, yeah, I don't know what to do with that magnesium bromide. B is going to lose its shit over the magnesium bromide, make an oxocarbenium. So A plus B prime in the presence of magnesium chloride will give us AB prime or B prime B prime. But we're not going to have any A as the electrophile because A is not going to be activated by that. So we still have a problem here. So we need a better way to differentiate. So there's two ways to do this. We're going to talk about one first, which is actually the more complex one, and then we're going to move to the simpler one, which is the way that you would do it. You would never do it this way because this is stupid. But this is something else we can do to actually do the glycosylation stuff. And that's that we can switch the protecting groups. So acetates are inherently electron withdrawing if you have them on oxygen. You actually see this by NMR if you actually ever look at, if you look at NMRs of acetates, the H on the I can't draw H's on these carbons because I haven't done it, but the H on this carbon, for example, if this is galactose, I can't remember if this is glucose or galactose. I'd have to flip back. But let's say there's an H there. That H, if that's an acetate at that position, is going to be like a whole ppm difference in NMR shift than if it's an OH. It actually has a very, very significant effect. And so what that does is if the whole sugar has acetate protecting groups, it means that there's less electron density on any of the oxygens. So this OH and this OH, their reactivity, their nucleophilicity is decreased compared to a normal oxygen because the acetate that's on the rest of the ring is pulling electron density out. So this is as a nucleophile. I'm going to be really clear because this is going to be the opposite of these things as an electrophile. And I think we already talked about armed and disarmed donors. And I'm talking about activated and deactivated nucleophiles. I should write down nucleophile. I actually did. I am going to just write that explicitly instead of in brackets because the brackets was stupid. So poles E minus density away from any OH. Activated are things like ethers, benzyl ethers. Or even better, silyl ethers. donates E minus. So these actually become more reactive than a standard OH. So what we could do in addition to doing this A-B thing is we can swap the protecting groups on A from acetate to benzyl. So this is really stupid. It's going to take a few steps, and we'll go through them on a later class. I'm not going to go to them all right now. I want to make sure that I'm drawing the right molecule. Nope, stop it. Just remember what A was. A is ultrose because that was stupid. I'm regretting using ultrose already. And now this is going to be more reactive. And an acetate protected. Ah, shit. I think it was galactose. Because we have this activated versus deactivated nucleophile. That makes sense. So now if I mix these two together, I'm going to make sure that this guy's the electrophile because of that. I'm going to make sure this guy's the nucleophile because of all of that. And so I'm kind of stacking a deck. That's the stupid way to do this. The smart way to do this is to put in a protecting group. So if I take B prime and I add in a protecting group to protect the C6 position, actually it's not imidazole. It's just the base that gets used for this. Then we can make B double prime. You could put, you'd have to be careful about putting in a benzyl. I don't know, Samurai, did you just ask that question?
Yes, yes.
You'd have to be careful because if you put a benzyl on that, you'd have to take that benzyl off without taking any of the other benzyls off. It's always good to try and pick something that's, well, I'll talk about this. It's always good to pick stuff that's orthogonal to everything else that's present so that you can selectively remove whatever you want. In this case, we can selectively remove silicon later. So if I take that and I take, going back to A, which was just the normal ultrose with acetates, I don't need to fuck around with slight differences in reactivity because of acetates versus benzyls, which is true, but still mild, because now I solved this problem. This is not a nucleophile. I block that. It is no longer an alcohol. This is the only nucleophile in solution. This I can activate selectively using magnesium bromide. Chloride will work too. Let's stick with the bromide. This is not going to be activated under those conditions. So there's only one possible outcome for this reaction. And that's oxocarbenium formation here. This guy acting as the nucleophile. So what I'm doing here is I'm trying to control, and this is what's going to be really important, what we're going to be talking about a lot the week after reading week, because I think we're going to get done with glycosylation stuff today. Then I'm trying to control both the nucleophile and the electrophile. I'm trying to decide the regiochemistry, so which oxygen is attacking, and the stereochemistry, am I getting the alpha or beta product? I'm controlling which building block is reacting by having activated this one. I'm controlling if I'm getting alpha or beta by making sure I have a C2 acetate here, so that when I do anchiomeric assistance, I will deliver beta. And I'm controlling which one's the nucleophile by blocking this one. So I basically reduce the options of these molecules down to nothing. They can do one thing, and that is react the way I want them to. There is no other choice. It'd be even better if I remember. I've gone from like, that's not ultros. I just randomly drew that vertically. I tried to pick my sugars so they didn't get in the way, so they're easier to draw. Not because they're of any real importance. This is not like an important disaccharide. I doubt this trisaccharide has ever even been made. It's amazing how many trisaccharides there are. And once you start wandering off of like galactose and glucose and mannose, almost any trisaccharide you can think of has never been made by anybody ever, which is pretty cool. And even with those, we recently made a disaccharide of galactose and glucose that we're publishing, and it's never been made before. We needed it because it was like for some immune system project. But just fundamentally, we made a new disaccharide. It's just two sugars. Like, come on, how many? And it's like two of the most common ones. But yeah, never been done. Okay, so we can make that because we've controlled everything. Now I've got this. If I remember, I want to put an isopropanol here. I can do that, or I can actually leave that to the last step and stick the next sugar on. So, let's stick the next sugar on just because we can. So I need to deprotect the TBS. We'll talk about that in my next lecture. I'm going to use tetrabutyl ammonium fluoride. TBAF is not actually that much quicker to write than N-tetrabutyl fluoride, but we write TBAF. And so that's going to, I wish I knew how to use the selection tool to copy and paste things. Or rather, I wish I knew how to use it quickly without screwing everything up 20 times.
I'm not sure how it works on PowerPoint, but on OneNote, you just select it with the tool.
Yeah, no, it works great. Exactly. It's just I always fuck it up. It's just it will take me longer to do that than to draw this out.
Fair enough.
A more competent person like you could probably do it a lot better. It's just I suck at it.
I'm glad that you think I'm competent, even if it's not true.
Very competent. Okay. So we've got that. Wish I had more space on my OneNote. I use this instead of OneNote because these convert nicer to PDFs. Like OneNote, you have to convert into PDFs, and what I find is whenever I used to do that, the page went always straight through a structure. Because in OneNote, I was never able to figure out, if you know how to do this, Paul, I'd really appreciate it, how to line up where the pages will begin and end if I print this as a PDF, just like open.
I don't, but I can try to figure it out.
Yeah, that would be nice in PDF. It'd be nice in PowerPoint because it's like infinite scrolling, right? You don't have to like switch pages, and
yeah,
I don't like that about PowerPoint. So what we can do is we can take this, we take the final sugar, and I think we'll just do this one conceptually right now instead of having to actually solve the problem. So that's what we had. Now here we need to activate this. We know how to do that. Let's turn it into a sulfone, because why the hell not? You can use a sulfoxide if you like, but you can do a sulfone. And then trying to control the nucleophile. So our nucleophile here is an OH, but we have an OH here. But this is a primary OH. And so a primary OH is more reactive than a secondary. So in this case, we don't need to play around with protecting groups. You can, like, be my guest, and I probably would because I'm paranoid. But theoretically, you don't need to. You will get the primary reacting about 10 times faster than the secondary. And so you'll get like a 9-to-1, 10-to-1 ratio. And that's good enough. I'm happy with anything over about 2-to-1. So I think this takes us to the final product. We use that with magnesium chloride. And so here what we're doing is we're not controlling it through choice of protecting group, we're controlling this through the inherent properties of the nucleophile and just how sterically hindered it is. So this example we do is we cover a lot of things. We've sort of looked at the deactivated and activated rings by choice of protecting group. We're able to control which of the activating groups, which of the anomeric activating groups are activated based on the oxidation state of the sulfur, and we can oxidize up, or it's actually kind of hard to reduce down as possible to do. But you tend to reduce a lot of other things too. And then we also take advantage of the inherent reactivity difference between a primary and a secondary alcohol to give us the kind of reaction we want. Okay. So what I want to do next is talk about, I think, the last one that we're going to do, the last glycosylation strategy. There's a lot more, but they're not really that important. Trichloroacid Imidates. Forgive me, I am always going to abbreviate this as TCA because that's just too many things. So what the fuck is that? Well, it's this. So the reason I'm discussing these guys, so far, I think the big advantage of the glycosyl sulfides I just talked about is their stability. If you want to carry something through multiple reaction steps, they're great. Like the thioether ether is a rock. Like you can oxidize it, and you have to treat it with like strong acid and halogen for it to fall off. Like it just, you can do a lot of functional group conversions on the rest of the ring, play around with what else is going on in the rest of the sugar, and that's fine. The halogens are really easy to use. That's why we start with glycosyl bromides. I still use them when it's simple, but you can't. They're very unstable, so they're kind of a pain in the ass. The glycals gave us all that flexibility over will he or won't he have a substituent at C2, because we ended up with that halogen there, and we could displace that, or we could use a epoxide and avoid the halogen, or we could stick a nitrogen in, or we could burn off the halogen using radical chemistry. So we had lots of options with what went on at C2 with the glycals, which is kind of handy. What's really strong with the trichloroacid imidates is they give us really good stereochemical control over the glycosylation. They are unstable. So if you're lucky, you can pass these through column chromatography, but most of the time they'll decompose on you. But the good news is they come out pretty clean. They're able to be made pretty clean. At least theoretically give control. The truth of the matter is they work really, really well for glucose and less well for all the other sugars. So I'm going to kind of invert the way I've done this. So far what I've always done is talk about how to make these and then talk about how to react them. I'm actually going to start with talking about how to react them first. Because I always need to look this up. Yeah. Okay. So if we take and I'm going to put benzyl protecting groups here at C2. If I take that TMS triflate and a nucleophile, I get that. And if I take CCl3. TMS triflate and a nucleophile. I get that. So it's a pure SN2 process, which is really handy. Now, if you want, you can take don't know why you would. I'd say don't. I don't know why you would, but we've done it. So apparently, we're not all that bright either. If you take that, either anomer, doesn't matter which one, you treat that with BF3 etherate, which is another Lewis acid, then you just get a nucleophile, mostly. It doesn't matter what ratio you start with, because this goes through an SN1 oxocarbenium. So by choosing the Lewis acid here with these TCAs, we can go either SN2 or SN1. Now, SN2 always gives you more control. You almost always want to do the SN2. The SN1 is more reactive, and in our case, the SN2 just didn't go. The TMS triflate just didn't work. It just wasn't strong enough. It was a stupid molecule. I don't know why it didn't work. I'm still angry at this molecule. I've used this lots of times. It's always worked for me, and then this time, just no. But mechanistically, how does this work? Well, let's take a look at this guy. So, unsurprising, hopefully, to everyone, is if you attract it with TMS, you're going to make that. I'm going to sort of draw the product if the nucleophile came in. So let's draw this. And then I'm just going to draw it kind of as a close ion pair. So it's going to do the SN2. And I think this is probably an accurate way to describe this. I'll draw these as covalent, but they're all kind of dotted. So if we think about what we just made, it's that. And that looks like a pretty stable molecule. Like the whole TMS thing instead of a proton isn't great, but we'll replace that on a workup, so that's not a big deal. But the rest of this thing is just, it's kind of an amide. So it's very favorable to form this. It's a really good leaving group. And then our nucleophile, of course, is going to come in SN2-like and allow that to fully dissociate. And often your nucleophile will have a free OH, like it'll be an alcohol or something, and that's going to give you the hydrogen that will replace this TMS group. So okay, nucleophile will recover the TMS plus, which will go and do another catalyst cycle. So I'm going to call this nucleophile H, like it's got an H bond. Now it's just nucleophile. And we generate that byproduct. Okay, whoop-de-dee, it's an SN2. We've seen that with the fluorides. We've seen some other SN2s. You can do it with the bromides. What's really special about the trichloroacid imidates is that you can control whether you make the alpha or the beta trichloroacid imidate really easily. And so when we saw how to make the alpha and the betas of the other ones, you had to really fuck with conditions. Here you don't. And I actually like this next one, my next slide, more than I actually like anything else about trichloroacid imidates. Like it's the thing that gets me excited. Let's see to find the right slide. There we go. And that's because if I take glucose, benzoprotected, I treat that with sodium hydride in THF with trichloroacetonitrile, which is where our trichloroacid imidate is coming from. I don't have a temperature here, but I'm going to guess 0 degrees Celsius. %93% yield of the alpha. Now, if I take the exact same molecule and I treat that with potassium carbonate, THF, trichloroacetonitrile, 0 degrees, and then water is workup. We'll show us mechanistically why that's important. You get 95% beta. So we get 93% alpha with one base. We get 95% beta when we use another base. All we're doing is changing the base. To me, that's really cool. I find that really, really cool. I don't know if anyone else finds that cool. I'm pretty lame. So, what is going on here? How can we explain this?
It's the salt and the hydride.
It's the salt and the hydrate?
Yeah, the base is working differently.
Right. Yeah, I completely agree. Why is the base working differently? What's the difference between sodium hydride and potassium carbonate?
Does one chelate somehow?
Nope. Okay. Good guess, but no. Is there a difference in the strengths of those bases?
Ooh, sodium hydride is stronger.
Yeah. That's it. Sodium hydride is stronger. Okay. So that's the information you need. Probably if you use butyl lithium, you could use that instead of sodium hydride, or you could use LDA instead of sodium hydride. You could probably use triethylamine instead of potassium carbonate. Wouldn't be as good. Like, these are the best ones for this. You get better yields this way. They're also they're both non-nucleophilic, which is good. But you could swap out for other bases of similar basicity and you would get a similar result. So mechanistically, what the fuck is going on? And I love this so much. Okay, so let's consider that we have mutarotation. Like, that's just a thing, right? We start with a free OH. We got mutarotation. Now, let's say you trace this with a base. Treat it with the base. Trace it with the base. We have that. But those two also interconvert. And now we know we want the O minus to sit equatorial, not axial.
Is there any ionic bonding going to happen?
Sorry?
Is there any ionic bonding going to happen?
Ionic bonding. Yeah, I think we're thinking about this maybe a little bit wrong. Maybe this will start popping in. Okay, so now let's consider that we've added this guy. Mechanistically, this is what happens. Same thing, just at the alpha, or vertical. And then H plus from water. When we add the water later. Okay. Now, in my fetish for thermodynamic versus kinetic processes, this definitely falls into that. So let's think about what we have here. So this is like the whole mechanistic route pathway of what's going on. Okay. So this is what I would call a fast equilibrium. This equilibrates quickly. The switching back and forth at alpha and beta alkoxide is basically instantaneous and really, really fast because it's mutarotation on steroids. Now, in both cases, you add excess base, and so this is essentially irreversible because you have a strong enough base in both cases, sodium hydride, potassium carbonate, to deprotonate that alcohol quantitatively and transport it down to the alkoxides. Okay. So now let's take a look at the product down here. And let's say there was an equilibrium between these two. Which one do you think is lower in energy? Which one do you think is more stable?
The left?
Alpha should be?
Sorry?
Alpha?
Yeah, alpha, right? You got a really good electron withdrawing group. Anomeric effect is super strong with this. This is the thermal product. This is then the kinetic product by definition. Well, it's not the thermodynamic product. But it also makes sense it's a kinetic product because if you're thinking about where the rate determining step is, it's this. And we know that beta alkoxides are less stable than alpha alkox. Like they're more stable, but they're more reactive too because they're more available. So this would be faster. So this is the kinetic. Faster. So it looks like we have a typical thermodynamic control, kinetic control situation here. It's just what's really curious is the base that leads to this product here is sodium hydride. And the base that leads to this product here is potassium carbonate. And sodium hydride is a kinetic base. It's a stronger base, but it's giving us a thermodynamic product. And potassium carbonate is a thermodynamic base, but it's giving us a kinetic product. That's weird.
Agreed.
Okay. So, what could be happening to explain this process?
Are we missing an intermediate? Should there be any intermolecular interaction? I don't know. Are we missing that part?
No, I don't think there's anything particularly intermolecular going on.
Does it have anything to do with the counterion? Or
Yeah, I think the counterion and more what's happening here, because let's remember what we've got. So when we're doing this with sodium hydride, we get H2 generated because sodium hydride H minus reacts with this guy to give us this, whereas potassium carbonate reacts with that to give us HCO3 minus. So I'm not sure counterion is the right term, but it's almost like what is this? What is the thing? So in this case, the hydrogen, it's gone. It escapes. That is irreversible. So if we think about this equilibrium here, I always want to make sure I get this right. In both cases, we're going to make this guy first. No matter what base we use. But if you have potassium carbonate present, you can protonate that nitrogen. Because this is pretty basic. If you don't have potassium carbonate present, if you have sodium hydride present, you cannot protonate that nitrogen. And the reason you can't protonate that nitrogen is there's no hydrogen available because it's sodium. There's hydrogen gas, and that's escaped, and it's gone. So what's happening here is we're kinetically trapping the kinetic product. So we're making this guy first, and then it's snapping up that hydrogen and making this product before we're adding the water. And once it's made that product, that's it. It can't go back. Potassium carbonate can't deprotonate that NH. We're done. So we're making this guy, and as it's made, it's transferring over pretty quickly. Whereas with sodium hydride, we don't have that source of hydrogen. We don't have that proton available. So we make this, it sits like this, and it goes, you know what, I'm going to try something else. Folds back over, and it goes, sits like this. And if I'm comparing these two structures, it's not the best thing in the world. It's not the strongest anomeric effect. But CCl3 pulls like crazy. Like it's just hauling electron density. And so, yeah, there's a full negative on this, but it's over on this nitrogen over here. So we can still donate electrons into this. So this guy's more stable than that. And those guys are in equilibrium because we're in sodium hydride. That TCA is adding, it's falling off because that N minus can't satisfy itself. There's no proton available. So eventually you build up a pool of this. So everything starts sinking down to this stuff here. This is the thermosync. And so when you finally introduce some water, that's what's present in the solution. Snaps up all the hydrogens, pumps out the product. So I think the thing to think here is to think these, I call this the thermodynamic product, and it is. I call this the kinetic product, and it is by appearance, but I have those backwards. No, I have those right. But the bases seem to go backwards. But it's because the base, this kinetic base, and this thermodynamic base, it's the conjugate acid that's really determining reactivity. And this is a thermodynamic conjugate acid because there's no acid. The H2 is gone, so everything kind of equilibrates. Whereas this is a kinetic conjugate acid because it's a very strong acid compared to the reaction solution. So I think all this is to hopefully, I think part of this course is to make everyone else feel a little bit as confused about thermodynamics and kinetics as I am. Because I just get confused about this stuff. Like this works, and this is why, and these details are why, but we start seeing why these words are a little bit unclear. Yeah, misery does love company. But the words aren't properly describing reality. Like using the terms kinetic for a process or thermodynamic for a process doesn't really explain the process because there's a lot of steps in there. We almost have to talk about whether an individual option that a reaction has at a given point is a kinetic choice or a thermodynamic choice. I'm not testing on this. But I think the outcome of this and why this matters is it does give us that exquisite selectivity on alpha versus beta, depending on which TCA we use. So what's really cool here is we can completely control whether we get alpha or beta. With the same starting material, we can get either the alpha TCA or the beta TCA. And then if we have the alpha or the beta, we can completely choose whether to do SN2 or do SN1 and lose all that hard-earned information that we just ended up trying to play around with the right base. So I think that is where I am going to leave TCAs. Like the one comment I got for TCA, the one real weakness for them is TCA's weakness. And that's they work best with good nucleophiles. Like that's true of everything, I guess, but TCAs especially. And that's because, let's just go back to reaction conditions. If I took, we made a beta TCA, benzo protect the sugar. It's a chloride. And I take, TMS triflate because I don't want to lose my stereochemical information because I'm not a moron. And I use ethanol. Good nucleophile. I always talk about nucleophiles being sticks or balls. This is a stick. It's unhindered, sterically unhindered. There's not a lot of bulk around an oxygen. The oxygen is readily available. This works great. Amazing reaction. Works well with a lot of sugars too. But let's say I pick a much harder to react nucleophile. So I pick, I don't know, some stupid isopropanol thing. TMS triflate, same thing. Now, most of the other sugars, it wouldn't have mattered. Restart that sentence. Most of the other glycosylation techniques, we wouldn't have differentiated between these two because we'd be going through a hot oxocarbenium, and it's like, yeah, you got a bit more stuff with steric stuff. I don't give a shit. I'm an oxocarbenium. I'm going to react with you no matter what. Last call at the bar syndrome. But TMS triflet, but the TCAs are a lot more selective because what we get when we make the oxocarbenium or the not oxocarbenium or what we have floating around is we make this. Not an awful nucleophile. So what can happen then is you have, okay, yes, it's not an oxocarbenium. So you have an ion pair. No, it's beta. Shit, that was on Y's. It takes up more space. So you just made this. You're really proud of yourself. Your flask is happy. But now you have this really bulky, shitty nucleophile, and you have a decent one. And so this guy, unfortunately for you, can come in and react. And that's dead. That's not going to react any further. You're not going to be able to activate that. You made a nice, strong amide bond. Like the whole point was, the driving force of this TCA was to make that carbon-oxygen double bond, which is nice. Carbon and oxygen love making double bonds. Now you've made it. and now you give me an amide. Like, that's just an amide. That's not going anywhere. You're not being able to cleave that. Uncleavable. So they work best with good nucleophiles because compete with poor nucleophiles. Okay, that is glycosylations. We have talked about halogens, Koenigsegg, we've talked about anomeric fluorides, we've talked about glycols, we've talked about sulfides, sulfoxides, sulfonates, and we talked about Trichloroacid Imidates. There's another 5 or 6 which have been used by more than one person, but I think that gives you far more than you need in a way of tools to think about this. And again, what I'm going to highlight is there are so many ways to do glycosylations because none of them are very good. They all kind of suck. And so often you need to kind of sample different methods to try and figure out what's actually going to work in your specific situation. And that's tough. So over the next week, by not this weekend, by next weekend, I should have a series of lectures. I guess to replace the one I missed, but it might amount to more like 2 hours worth of stuff. I'll try and keep really, really careful notes. So if you don't want to watch the video, you don't have to. And it's going to be on protecting groups, putting them on, taking them off, all the different things, and some of the strategies we can use to move protecting groups around so we unveil specific oxygens on specific sugars. At one point I was thinking about writing a book on this, and then somebody else who wrote a much better book than anything I would have written. So it's a brand new book. It's the first time ever. It was published in 2020, called Protecting Groups in Carbohydrate Chemistry, and I got really excited about it. So I'm going to be the library has a copy, but I have it, and you can't have it. So I'm going to pull from that for the notes, and then just from all the notes I've made about protecting groups in carbohydrate chemistry. So we'll learn how to basically unmask any given oxygen. And then I think the Tuesday we get back, we're going to be spending that class just doing problems together as a group. I'm going to shut up and just draw, and we're going to problem solve together. So it'd be good if you look at those lectures before next Tuesday. I'll try and have them up by Thursday night. So Friday, Saturday, Sunday to look at them. And then the midterm again is March 4th, which is the week after reading week. Okay. I'm done. Thanks, everyone.